spring break.
So, cool. Can I have everybody with me, please? Awesome. Web Work 9, at the request of Sophie, has been extended through tomorrow, so that's the improper integrals.
Thank you.
You're welcome. She's going to send me an email, and that's going to help me remember to do it.
I'll do it right now.
Thank you. That's because you needed me to remind you
Yeah.
about the email. Awesome. Thanks.
Yeah, I'll send it now.
Thank you. Exam 2 is next Wednesday. And it's going to cover volumes, so the rotational volumes, all that stuff. This will be like, I'll give you a bunch to set up and not solve, so you'll just set up the integrals. Improper integrals, so stuff with infinity, very basic ones. And then stuff that we're going to start today, differential equations. So these are all in applications of the integral that we're doing here. But this is fun. This is going to be really different. So the exam's going to be very different as well. Next Wednesday when you come in, I will give you the exam. You will work on it in class. You will walk out with the exam. And hopefully, in your best interest, keep working on it. Come back on Friday, finish it up, hopefully writing up, because like, I'm going to want it to look kind of nice. So like maybe, cleaning it up and stapling it together by the end of the class on Friday and turning it in. If you get it done before then, you can just come to class and drop it off too. That's totally cool. It's not going to be a crazy like sometimes take-home exams are insane. This should not be like a 20-hour endeavor. God, I hope not. I hope it doesn't take more than a couple hours, really. That's my goal. But you'll have lots of time to think about it. There's multiple versions of the exam going around and all that stuff. Does this sound okay? Good on this? Yeah? Cool. Alrighty, hey, I want to tell you a story. So today we're going to start talking about differential equations. Probably one of the most important things you can know if you're going to be a scientist of any kind, if you're going to be an economist. They're literally everywhere. Differential equations are the language of science. A scientist thinks in differential equations. You want to understand something about the world, you first relate rates of change that you've observed, put them together, and then solve that differential equation to come up with an actual formula. But differential equations, this is really the language of science. If I can spell language, apparently I can't even. Oh my God, God, why am I? Is that the word language?
There's not a second N.
There's not a second.
There's
Yeah.
not a second.
Okay,
No,
okay. Oh God, that's why it looks so weird. Thank you. Okay. Woo! Thanks. It sure didn't look right. Language. Yeah, I guess that ain't it. Language of science. Apparently, I need like just the basic language. So I'm gonna show you what I mean by that. Let's consider a scenario. So here I've got just a spring hanging from a ceiling or a roof of some kind. So this is a spring. Let's talk about springs just a little bit. This spring we're going to make some somewhat unrealistic assumptions about. We're going to assume we have what's called a linear spring. And what that means is that if I apply a force to the spring, so I put a mass on the end and it gets pulled down by gravity, or if I pull on it myself, the force required to move the spring X meters, centimeters, inches, whatever, is just directly proportional to the force. So this is a constant here. So it's a linear relationship. This is the amount of extension on the spring. And this is the force. You can think of this two ways. This is the force required to extend the spring X units. Or you can think of it as the force the spring is exerting backwards as well, right? So when I have a spring, well here, let me attach a mass. So now I'm gonna go to this next scene here. Let's say that the spring is L units long when it's compressed. So that's the compressed spring, doesn't look compressed, looks pretty loose, but that's just raw spring stuck onto a ceiling. I attach a mass, M, to it. So in the next scene here, I'm going to attach a mass to the end and it's gonna pull down on the spring. So let's put a mass M right here. So this mass is pulling down with the force of gravity. So it's just mass times gravity, right? A lot of this is coming back to Newton's second law, which says that if I apply a force to a mass M, it results in an acceleration of that object. So this is a really key law for getting a lot of stuff done in terms of writing differential equations. Is this all making sense so far, where I'm going with this? Kind of some kind of basic physics in a way. You might not have ever done what we're about to do here. So it's pulling down, spring's pulling back up, everything's at equilibrium. So this is really almost at equilibrium. Well, I guess this is actually equilibrium. But let's measure. So now originally, this spring was L units long, and then I attached the mass, and let's say that it's stretched at S units. So S is the displacement, the downward displacement after I put the mass on the spring. So this whole distance here is L plus S. Let's just make a little note. That's just L plus S right there, all the way down. So now, let's imagine that the mass has been disturbed. In other words, I've come into the system and I've either pulled down on the mass and released it, or pushed it up and compressed the spring and released it. Maybe even given it a little upward velocity, or pulled down and then pushed down first or pushed up. So all sorts of things can happen here. But let's go to the in motion. So let's see, this is compressed, this is attach the mass. Don't do anything else. And then in motion, let's look at the case where we've come down a little bit. So that spring is kind of changing its nature a little bit. So I'm gonna come across here. So this distance here that we moved, remember this is L, this is S. And now we've got a new displacement, we're gonna call that X. So X is the displacement from equilibrium. And what we're going to say is that extension, so down in this direction, this is X positive. If we're compressing past this point, we're just moving back up and lessening this S here, that would be X is negative up here. And this is X equals 0, right at equilibrium. So let me know if the story doesn't have enough detail for understanding. That sentence came out weird. I'm having language troubles today, I guess, apparently. So let me know if any of this needs clarification. I really want you to understand it. All right, so this thing, once this is gone, now this thing's in motion. So now the system is in motion here. And we're going to go to Newton's second law, that let A equal the acceleration of the mass and from Newton's second law, the mass times that acceleration equals the sum of forces acting on the mass. So now we just got to figure out what are the sums of forces here. Actually, let's do another thing. How can I write A in terms of the displacement X? So if X is displacement, what's X dot? Let's go through this. What's X dot here physically? Oh, sorry, you might not know what that means. So when I write this, x dot is the derivative with respect to time of the position.
So that's the acceleration.
One back up, almost, not there, velocity.
Velocity.
Yeah, yeah. So this is the velocity. And sorry about that notation. So make this note that x dot, that's instead of like x prime. So, you know, when we do y prime, that's derivative with respect to x. When you do dot, that's derivative with respect to t. Very classic in all the sciences. So now, Lloyd, when I've got x double dot, that's acceleration. That's the rate of change of velocity. So that's acceleration. So A can be replaced with x double dot. That's bringing us back to now understanding something about x. It's putting x into this equation. So let's bring this down. Let me just bring this down here. So what we're going to get is mx double dot. This, so again, let's put that notation over here. That is the second derivative of x with respect to t, is equal to the sum of the forces. So what is happening here? Well, there's only two forces acting in this system. There's gravity pulling down, and there's the spring either pushing down or pulling up. So mx equals force of gravity plus the force of the spring. And we just got to get our orientations right on this. So what do we got here? So we got mx double dot equals, well, this is, I've already set up that this is kind of my positive direction. I've said that extension is positive. So what we've got is mg, the force of gravity. So that's force of gravity. G is just the gravitational constant for acceleration. So this is, if we were using meters, it's 9.8 meters per second squared. If we were using feet, it's 32 feet per second squared. But the force of gravity is just pulling down on this thing. This is actually just its weight. That's what your weight is, right? Your weight is gravity pulling on the mass that you possess. So weight is an interaction with mass and gravity. So we've got mx double dot equals mg. These are the same sign because when x is positive, gravity is working with it, or when x double dot is positive, when we're accelerating to extension, gravity is working with us. The spring is going to change that. We're going to actually have the spring working against us. So think about this. If x is positive, if we're accelerating, the spring is slowing us down. The spring is kind of always working against us. So when x becomes more positive, the spring force works this way. When x becomes negative, the spring force is pushing it back down. So when we're compressed, the spring wants to push back in the other direction. So here, the spring force is determined by this thing. This, by the way, is called Hooke's law. That's a K there. Hooke's law. It's really only true for very small x. In general, most springs aren't linear. This becomes a much more complicated thing for extension beyond just a little bit. But we're just pretending here. We're getting the basic ideas. So this thing here is going to be the K times extension here. So we just have to figure out, what is our extension? Well, our extension is going to be the extension that came from the mass itself, S, plus x. So notice here that the full extension is s plus x. And then when x is negative, that shrinks that quantity to be less than s. When x is positive, it's more than x. So this is s plus x in here. And then, times k, excuse me. So this is k times the extension. I wrote it as backwards. Let me rewrite it. Extension times k. That's about it. Whoa, come back. Can I answer any questions about just that basic equation? Just understanding how I got it. So let's simplify. Looks pretty interesting. So we've got mx double dot equals mg minus sk minus k times x. So I'm going to stop here for a second. This is interesting here. That quantity right there, we can do something with. Come back to equilibrium. So when I first attach the mass, things are at rest here. So that means the force of gravity, mg, is precisely equal to the restoring force of the spring. So that's acting like this. That's ks is pulling up this way. It's equal to mg. So at equilibrium, ks equals mg. So these two things right here are, yeah, exactly. So this equals 0 because at equilibrium, in other words, before we even moved things, we had mg equals ks. So this is gravity, and this is the spring. This is force. So those two cancel. mg equals ks. So now here's what I got. Check out this beautiful equation. And there should be a, oh no, not yet. So I'm going to move everything to one side. It's x double dot plus kx equals 0. And here we go. This now describes the position of the spring at any instant. This is a differential equation. So I want you to notice a couple things here. There's no friction in this scenario. It's very unrealistic in some ways. There's no friction at all. So this thing never loses energy, the way the system works. So x dot is actually, if we had something like this, let's put a little mu x, this would be a friction force. Think about that. When you imagine yourself in a pool, you're in a pool and you're up to your chest in water. Think about how easy it is to walk slowly in the pool. Right? When you walk really slowly, no problem. Have you ever tried to run in a pool? Anybody ever tried to run in a pool? Yeah, the minute you start trying to accelerate, you feel the force coming on you. So if you're trying to run and you have a high velocity, you're going to get a lot of resistance. So friction is actually proportional to velocity here. So let's just put a little proportional to velocity. We're not going to add that in here. There is none of that here. To get friction in a scenario like this, you would imagine you had it running in a water. You had your spring like moving in water or some gel or something like that. Something viscous, some viscous fluid would create friction. We're not going to worry about that. So let's take this equation right here. Let's just talk about that for a second. And it's going to lead into what does it mean to be a differential equation? What does it mean to be a solution to one? So here is our equation. Mx double dot plus kx equals 0. So a solution to this is a function x. So this is a whole new world. You've got an equation, and instead of getting numbers out, like the roots of a polynomial, we get out functions. These things are living. You get a whole range of motion out of this thing. This solution to this is a function x of t. Let me give you a quick example. E.g., if our equation had, let's see here, a mass equaled 1 and the spring constant was 4. It's just, I'm just making some shit up. But let's say we knew this, and there's units that go with this. This is like newtons per meter or newtons per whatever, it's force per extension unit. And this is just mass, so grams, slugs, whatever you got. Then our equation is going to look like this. X double dot plus 4x equals 0. So this now models the spring system. If I could solve this, I would have an equation that would tell me the position of the spring at any instant. We're not going to learn how to solve this kind. We're going to learn to solve a simpler one. This is actually called second order. So this is the second order differential equation. You can say diff EQ now. Because the second derivative occurs. Because there is a second derivative. We're only going to work with first order, but I kind of wanted to just show you this so you've seen it because it's a cool derivation. And the solution to this, x of t is going to equal some constant times cosine of 2t plus c2 times sine of 2t. Now in the web work that's going to open up, you're going to have a problem that says, show this is a solution to this for any C1 and C2. So let's put a little note here. C1 and C2 are arbitrary constants. Now let's just look at this for a second. What does this look like? This is sines and cosines, right? So it's oscillation. That makes sense. I've got a mass spring system, and as time goes on, it's going to move up and down, just like a sine or a cosine would. So this makes total sense that it's our solution, but how do you verify that? So, to show this is a solution, what we need to do is find all the derivatives that occur in the equation, plug them in, and show that this is true. So what I need is the second derivative. I'm going to find the second derivative of this. I'm going to replace that with this. I'm going to take 4 times the original function and show that when I add them, I get 0. So what we need to do is, step 1 is find all required derivatives. So we need x dot of t and x double dot of t. Hey, could you do those for me? You guys know how to take derivatives. You might not know how to derive a mass spring system. Or you didn't, but you do now. Could you just find those for me, please, friends? Oh, oh, that's right. We already did exam correction. Sorry, that's another class. Thinking about there were some chain rule issues on the last one. Doing that, I should get this warmed up. Really? Good. Come on, Reach. It's looking good on our first derivative, sanity check. Those 2's come out because of the chain rule. Cool. You're going to have to do exactly this on the web work. You're going to have to find the first derivative of something they give you. It's going to be a lot like that. And if you if there's no questions on this, but if there are, I'm happy to take those. So what we notice then is that if we take x double dot of t, this equation, plus x of t, so let's write this all out. We're going to do the computation. X double dot is this formula. So there's that. So that's x double dot. And then I'm going to plus the original, 4 times the original, right? Because that we had this 4 there. So plus 4 times the x of t that we started with. And do you see that everything cancels out nicely? So make sure you see that. I expand this 4, bring this 4 into here. You're going to get negative 4c1 coses plus 4c1 coses. Those are going to cancel. And similarly, the 4c2 sines are going to cancel because they're opposite sign.
Did you mean to pull a 4 out or 2?
Where at? Here?
Yeah.
No, okay, I'm glad you asked that, Sophie. So I'm going back to the original equation that said take the second derivative plus 4 times the original. So that's where that 4 came from.
Okay.
Yeah, that's a really good question. So make sure, believe that, convince yourself that what I've got there is true. And if not, ask questions like Sophie did, that yeah.
What if our starting K wasn't 4?
Oh, then this wouldn't be the right solution. So if I had a different K, so for example, here I can give you something that might be more satisfying to you. If I divided through there by m, and I did this, and that's okay because the mass is positive, then the solution here would actually be of this form. So the general solution would look like this. Yeah, really good question. So that was a really nice question. Thank you for asking. So now you could do it for any K and M you want. Is this resonating? Yeah. All right, I'm gonna trust you. Slowly walk to doing some other things here. Let's do one more example.
So our solution then is just 0, that's it?
So the solution is this. This is the solution.
We were just proving
We were checking that it was a solution.
Oh, gotcha, okay.
Yeah, cool. I'm glad you asked that. You're asking tons of awesome questions today. Thank you. The check will be in the mail. Beautiful. So yeah, just checking to see that that is a solution. Let's take a look at one more. So that's an example 1, and I'm just trying to show you how you can think with these things more than anything. Let's think about exponential growth or just growth of a population. So here's another example. Let's let P of t equal the size of a population of bacteria. Just a really simple organism at time t. So let's think about how this works. If I've got, let's say I've got a little petri dish here, right? And I've got some bacteria in it. And I've got, do bacteria, how do they split? Yeah, they split, they do mitosis? Okay, beautiful. Oh, awesome, that makes this easy. So if I've got one bacteria and it takes, I don't know, a certain amount of time for that thing to split, when it goes from 1 to 2, so let's call that delta T right there, the rate of change here is we increased by a size of 1 per delta T. So this is This is the rate of change here. Rate of change if one initial bacteria. But what about the next step? So this bacteria split into two, and then in that same time frame, each of these is going to split. So that happened over the same amount of time. It always takes bacteria, I guess, this probably roughly the same amount of time to go through mitosis. So now what is the rate of change here? So rate of change in the population is what I mean. We went from 1 to 2 here, but here we went from 4 to 2. So I actually have 2 more. So I have 2 over that delta T. And this is the rate of change if there's 2 bacteria. And then on that next step, when each one of these splits, we're going to go double, 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 double. So each one of those splits, what's the rate of change in that time frame? So here, what's the rate of change?
4.
Exactly. Yeah. And notice that the rate of change is actually equal to the number we started with. If you start with 10 and they double, you've got another 10, right? So your rate of change is always going to be equal to the current proportion, or the current population. So here, let's just write this out here. Rate of change equals 4 over delta T. So we can hypothesize. So what you could do is, you're a scientist, you observe this. You note, oh wow, the rate of change of the population seems to be directly proportional to the current population. So I just created a differential equation by observing how the change relates to the current state of things. I can now write something beautiful and powerful. Let me know if that makes sense. And that K, we don't know what K is. It's some proportionality constant. Here it kind of looks like it's 1, you know, depending on what T is. But this here, so if I wrote this as a diffeq, I would write P dot minus Kp equals 0. Notice how in these differential equations we suppress the independent variable, and we just write it in this beautiful form here. Now, if I could solve that, I would understand something about the population. If I can solve that, then I'll have a formula, P of T equals, that'll give me the population at any time I want. Notice I can't get that from here. I just understand how things change. But if I solve that, in fact, here's a solution. It's a constant times e to the kt. So this is the general solution is this. And here's how I check it. What's the derivative? So here's the check now. Take the first derivative. P dot of t is going to be c. What's the derivative of e to the kt with respect to t? What's the derivative of that?
K e to the kt.
Beautiful. So k comes out in front. So that's P dot, it's ck e to the kt. Let's plug it into the equation. Plug into, let's call this star. Plug into star, and I'm going to replace P dot with that expression. So I get ck e to the kt minus, this k came along, times the original solution, which is just c e to the kt. Notice that that just is always 0. So that's the solution. And that makes sense. If you look at that, that's just exponential growth, right? So c e to the kt looks like this. When t is 0, you've got c. Looks like c would be your initial population at time 0. So we could even get a little fancier right here, and we could say at t equals 0, we have P of 0 equals C. So C equals initial population. I'm sorry I'm blocking your way here, Alan. Get out of the way in a second.
Oh, you're good, you're good.
Okay, cool. So I could even go, population at time t equals initial population times e to the kt. This k needs to be found, but we need data. We need to understand how much, what is the population at a certain time, then we could solve for t. We're not going to do that shit. That's not part of our goal here. These are two examples of differential equations being built from observations about the physical world. This is the kind we're going to focus on. This is a first order, because it only has a first derivative in it. And that's enough. Yes, Abraham?
How exactly do we know that PT equals CE to the KT?
Well, we're going to learn how to actually solve that sucker, so you'll see how to solve that yourself in just a little bit. I just know it because I've been like doing it for a long time, right? So I've proved to you that that is the solution, so you believe me on that front, but I will show you by the end of the hour how to solve that. Sound good? Awesome. Any other questions? I hope I will. That's my goal. Looking at the, yeah. Yes?
So you got that equation by just prior knowledge, like P of T. Okay.
Yeah. Right now, it's just I know the right guess.
Okay. Cool.
Yeah. So we haven't talked. You don't know anything about how to solve these yet. Actually, let's just get into that. So yeah, let's just get into that. So let me get us focused again. We will focus on first order diffeqs, DEs. And we'll never see a derivative higher than the first derivative. So everything we're going to see will look like this. So we'll have either dy dx equals some function of x and y, or we'll have dx dt is equal to some function of t and x. And this means that the only derivative that shows up is this first order one. There's no derivatives in either of those functions. In particular, now this is like, I'm teaching this class right now. This is MT360B differential equations. We spent the first month learning how to solve these in some situations, but there's like a million situations. And you have to kind of like look at the equation you have, figure out what kind it is, and then approach it with a technique that was built for that kind of equation. So this is a big field. Like some of these we can't even solve at all, except with a computer. On Wednesday, I'm going to show you how a computer would solve these. And we're going to talk about that. But today we're just going to focus on how does a human solve these. So we will focus on a very particular type. We will focus on what are called separable differential equations. Now separable means that this right side is the product of a pure x function and a pure y function. So i.e. the equation looks like, or can look like, I've got dy dx equals a pure function of x times a pure function of y. There's no mixing here. Pure x thing times a pure y thing. Or, if I'm over here, I've got dx dt equals a pure t thing times a pure x thing. And the separation is actually part of the solving process. So what we're going to do is the following. You get that. I'm never going to give you one that's not separable and ask you to solve it. So just a heads up, on the web work that will be open, your first problem is a second order, like that first example I did. I'm not asking you to solve that. You just have to check the solution that they gave you. But then after that, you got to solve some stuff. So the method is this. Method for solving a separable DE. step one is separate the variables. And so this is kind of cool. This is the thing you've wanted to do forever. We're going to treat dy dx like it's a fraction that I can break apart. Or dx dt. Now is a fraction. Now I can multiply through by dx and get rid of that. So separate the variables. So in other words, get all y stuff with dy and get all x stuff with dx. And then, you know, or all t stuff with dt. Actually, I think that pretty much covers our cases over there. This is where people do weird shit, because this requires algebra. And you can do calculus, like it's funny, people can do so much calculus, people are amazing at calculus, can't do shit with algebra. They're very different skills, right? They're very different skills. So you could be a calc master, but not really be great with the manipulations at the algebraic level. That's okay. We're gonna take chill ones. So and then two, this is step two. So we're gonna get something like this. After one, you'll have something like this. You'll have all x stuff dx equals y stuff dy, or, and it doesn't matter what side those are on, or all t stuff dt equals x stuff dx. That's after separation. What you're going to do then is, this is application of the integrals, right? We're going to integrate each side. So step three, or step two continued is integrate, this is still step two, integrate each side. So what you'll get is something like this. I'll just write out the xy example. You'll do those integrals. You'll tack a plus c on. Plus c becomes actually super important here. So do this, do the integral. You'll have, so here you'll have an x function plus c. Then here you want to add plus c. I would add it to the independent variable side. So here it's x. If it was t and x, I'd add it to the t side, equals a y function. So that'll be your solution.
Do
And
we
so,
have to add the c to the y function as well, or is it just the x?
just one, yeah, I would just add it to one side, Abraham. I would add it to the independent variable side. So let me make that clear. Independent variable side. And now you could solve for y. You could solve for y equals pure x stuff at this point. But there's one more important thing, and this is three. If you're given initial conditions, some information about the system at some time, initial conditions, like x at time t naught equals x naught, or y at time x naught equals y naught, plug those into this and solve for c. Use these to find your c. So let's do some examples. That's kind of the rough plan. I could get more details in there, but once you see how this goes, you're going to get it. It's a very, very sensible and reasonable rhythm. Let me know how this all feels, if there's any questions. You all ask great questions, so always look forward to them. Let's do a bunch of examples. Solve All right, it's our first differential equation. We do x and y. The derivative of y with respect to x is x times y. And we have an initial condition that, and when you see it in this form, what this means is that when x equals 1, they're treating y as a function of x. When x equals 1, y is equal to 3. We'll use that after we do this all to find our c from integration. So step 1 is separate. And that means I'm going to bring the dy with the y, and I'm going to move the dx over with the x. So this one's pretty chill. Notice that it looks like this, and let me know if this makes sense or doesn't make sense. So I divided by y and multiplied by dx. And again, my goal is to just get all the variables of the same flavor together. And it doesn't matter what algebra I need as long as it's legit algebra. Could you please integrate each side? Tack the plus c on the x side on the right. And then if you're like super ambitious, solve for y in terms of x. Or if you have time to do such a thing. Well, I didn't use my notes at all. These notes were not useful. Gorgeous.
Yeah. Just in these, I would keep absolute values on there just for safety's sake.
Okay.
But
Yeah,
Cool.
beautiful. Yeah, so
E to the normal. This.
yeah, exactly. So Sophie, if you want, you can solve for y in terms of x if you want. You don't have to. No
I'll
pressure.
consider it.
No peer pressure here. Unless you're afraid to do it.
You got me there.
Yeah, I knew it. I knew I could get you with the negative enforcement. So the left side becomes natural log absolute value of y. The right side is a sweet power rule. We're good on this? Yeah. So this is actually a solution. Once I have this, I now solve the equation. You're done. This is what's called the general solution when you have that c in it. And no matter what c is, this solves that equation. But let's solve for y. And I'm going to use this rule. So let's use natural log of y equals this if and only if e to the triangle equals this. Remember, I wrote this down a couple times. That's some good shit. Use that in all your science classes, right? Like, use your logging like crazy probably in those things, I would think. So this is like just something to have for your academic life, except in like, you know, some RCC or something like that, where God forbid we do math. Can't have that. Boy, you try to do something like this in a RCC, people will be like having your head. They'll go to the president. I'll tell you some stories in a bit, but I've got some bad experiences with that. So this thing up here becomes absolute value of y equals e to the 1/2 x squared plus c. And notice that the absolute value of y is actually important here because this output is always positive from that e. But what I'm going to do is a trick. I'm going to note that this is absolute value of y equals e to the 1/2 x squared times e to the c. So I'm using exponent laws to rewrite that, right? Because you just add those exponents when you multiply these, and that's this. And I'm just gonna say this is c again. So one of the fun parts of differential equations is when you're doing this stuff, just absorb stuff into c. And so I'm gonna write this as my solution. And I'm taking the absolute values off because now I got a c that I could allow to be negative if I wanted. That's my solution. Let's check. Am I sure? Am I sure this worked? Well, let's review what it means to be a solution. It means that the derivative of this thing with respect to x is the same thing as just multiplying it by x to begin with. So check it out. What is the derivative? So let's check. What is y prime with our solution?
CX to the 1/2 x squared.
Yeah, exactly. So Voyn is using the chain rule, right? Take the derivative of the exponent, which is just x. Right? The derivative of 1/2 x squared is x. So that comes out in front. So I've got cx e to the 1/2 x squared. Notice that that is exactly the same thing if I took the original y and multiplied it by x, because the original y is this. So like you could look at this problem in a whole really weird way. You could say, find a function whose derivative can be found by just multiplying the function by x. It's a really interesting way to look at that, like almost like a linguistic way to think of what that means. Any questions before I do the condition? Can we change this to a 0, please? Just to make life easier. Everyone will be happier if there's a 0 in there. So what this means is that when x equals 0, y equals 3. So after the general solution, so now, and you don't need to do this checking thing. You can trust the method, but if you doubt your solution, you can check it. Now find c using the initial condition that x equals 0 and y equals 3. So I just plug those into the solution. So plug x equals 0, y equals 3 into y equals c e to the 1/2 x squared. What you get is 3 equals c e to the 0. And e to the 0 is 1. So c is 3. And then I just summarize by putting that back in. So my particular solution here is this. This is our particular solution that satisfies the initial condition. We'll just practice this a few times. Let me know if there's anything I can clear up. This is it, right? It's just like now it comes down to your ability to separate and integrate. So let's practice that. Solve. Let's not do particular, let's just do some basic things for a while. dy dx equals x squared y cubed. Can you solve that for me, please? And if you get really super excited, find y in terms of x. I'm gonna run to the restroom because this is the time of day I do that. For class, I think. I'll be right back. the separation we all did. Yeah. I would convert that to a power rule. Exponential. So far, so good. Power rule on both sides, really, really quite lovely, right? This goes to a -2. This goes, and I'm gonna always add the C to the independent side, so I'm gonna add it to the other side. How's that look? Yeah? Questions on any of that? No? Anybody solve for Y? Maybe, no? No? No, Alan? No? No? All right, well, let's do it together. You were just waiting for me to be kind. I appreciate that. It's very generous of you. So to solve for Y, I'm going to multiply both sides by -2 to just get that shit away from the front of the Y. And watch this. I'm absorbing negative. Instead of writing -2C, I'm just saying, it's C. I'll figure it out at the end. It gets to absorb everything. It's really fun. I mean, you know, all relative. And then this over here, I would write that like this. It's 1 over y squared. Like so. And that means to get y squared, I have to flip both sides. And then I have to take the square root. So I'm going to be really careful here. And I'm going to put plus or minus because I just took the square root. I don't know if it's plus or minus here. Actually, we're going to do something here. So this is decided when we get an initial condition. Let me just stop for a second. Does that all look kosher? Make sure that all looks good, that you agree, and that given the amount, given some time, you would do the same thing. Abraham, yes?
So let's say we weren't given an initial condition, which one would be like the answer?
Yeah, I would just put plus or minus and leave it, yeah, and then that's like kind of indicating that there's a choice to be made. Good question. So let's talk about that. So the plus or minus is decided depending, now I'm just writing what I just wrote down there again, depending on initial y value. So what I mean by that is, e.g., if I had initial conditions, ICs, call it initial condition, if I had x equals 0 and y equals -1/2, then I'm going to go for the negative branch of this. So this indicates use the negative branch of square root. So what I would do here is I'd say, because there's no other way, like if you put a plus in front of this, there's no way y could be negative. It doesn't get the chance, it can't if there's a plus. So I put the minus in front. So we're gonna have y equals minus square root of 1 over -2/3 x plus c, x cubed. And then I plug it in, I'll let x equal 0 and y equal -1/2. And I get -1/2 equals negative square root of 1 over c. I picked a nice, so letting that x be 0 made things sweet. And if I just say c equals 4, does that sound? Check that out. Square root of 1/4 is 1/2. So c equals 4 there. And so my final solution, so my particular solution is going to be y equals negative square root 1 over -2/3 x cubed plus 4. Done. Yes?
Does C not absorb the square root or anything?
Once I go to solve, that's what an awesome question. Once I go to solve for C, once I've got to this final solution, and then I'm using initial conditions, I want to stop absorbing. Because otherwise I'll lose information about the relationship between C and the other quantities.
Okay.
Does that make sense?
Yeah.
Yeah, so awesome question.
Will
Yes.
there ever be a case where you need both the positive and the negative roots?
No, not unless there's a problem where it says, what if the initial condition was this? What if it was this?
Okay.
So that, there might be one of those in the web work, I can't think, but that's the only time, so, you know. Other questions?
When's that web work open?
It should be open now. So, we're gonna actually end a little early today, but I'm gonna say a few things about that web work. I would, like, first off, finish up the existing one, right? Finish that up. But on the web work, it's web work 10, I believe. You can do question 1. So what I would recommend is question 1, and then you're gonna see these plots. Ignore those for the time being, because we have to talk about that. We'll talk about it on Wednesday. Yes?
It's not up yet, it's not on here, it doesn't have an open date on it.
Oh, well, I better fix that. Thanks. Could anybody email me about that?
I got it.
Thanks.
I'll just like follow up with other ones.
I'll buy you a Floyd CD or something. Thank you. So do question 1 and then skip over the ones with the plots, and then where it says solve, you can start there. You can just start solving like crazy, and you know exactly what to do now. All right, friends, cool. Wednesday I'm going to show you a little bit more, show you how to do the plot stuff, and then there's one thing that's not in the web work that we have to talk about, and that's Euler's method, and that will be on the exam. But it's pretty easy, and we'll talk on Wednesday. Yes,
Will
Avery?
we get a study guide for the exam?
Yes, you will. Always.
Awesome.
Thanks, friends. Welcome back.